Doesn't matter. Let's go.
Okay, great. So Fernando is going to present this, we think is the first battery simulation, battery manufacturing simulator that will be available in internet. I mean, you can use it from an internet browser by connecting to the artistic project website. And so we are very happy. It is a very big milestone of the project. I mean, releasing this is a main deliverable of a project. So then you will be able to play with these models that we were describing all around the week for free to produce results for your research, right? In particular, predicting electrode morphologies, electrode architectures in 3D by simulating the slurries, the coating drying process, and so on and so forth. Okay, Fernando, go ahead.
Thank you, Alejandro. Yes, so here I will present this new tool that has been developed here in the Artistic project that we call the Artistic Free Online Services. The idea of this tool is basically having access to battery manufacturing simulations that you can access to through your browser. So here I will cover at the beginning an artistic overview because this is fundamental to understand the scope of this tool. Then I will present the idea of the artistic workflow, where basically we bring together most of the tools and models and different results that the artistic crew has shown to all the attendants of this webinar during the last 5 days. Then I will briefly discuss the idea of building a digital twin, what is important and what's the idea behind that concept. Then I will go straight to the core of this presentation, which is introducing these online services and discuss what they are and how they look like, actually. So to do that, we are going to discuss at the beginning the computational infrastructure that supports them. And then we will explore a little bit the web interface so you can start to get acquainted with this new service that we will be providing. And in the end, of course, we're going to have some conclusions and perspective to put everything in the right context. So as I was saying, let's start with an artistic overview, basically what we have seen this week. We have all these wonderful people here working in different aspects of the battery manufacturing process. And for instance, on Monday, we saw Avos discussing lattice Boltzmann models for electrolyte infiltration, right? Then Alan talked about many things, but here I'm very interested in what he showed about coarse-grained molecular dynamics and the use of, finite elements to basically apply that to different parts of the battery manufacturing pipeline, and specifically to the calendaring process as well. Then on Wednesday, we have Theo discussing also many things, and among them, we can mention the different slurry and drying models that he's shown and discussed in great detail. And also on Wednesday, we had Mehdi showing us the art of meshing using INNOV in his case. So, of course, many other members of the artistic team show many other results. But I want to focus in the meantime in these 4 aspects to understand why they are relevant for these new services that we are now about to provide through the internet. So the whole idea then is bringing everything together, and I've been labeling this concept as the artistic workflow, where basically we can start with the slurry and drying models that Theo introduced to us, and then basically we can play with a set of initial parameters, namely the ratio between active material and CVD, the solid to liquid ratio, the particle size distribution, etc., and then go into our model and then basically get the structure of an electrode, right? But also then we have the different models that have been developed by Alain. So there we can actually use that same structure and also getting other inputs, of course. That's the idea of the arrow, the red arrow on top, saying that, of course, we are then getting another set of inputs and produce a new structure of the calendared electrode. But we saw what Mehdi showed us. So basically, through INNOV, we can take these different structures and generate the corresponding meshed equivalents. And then why not, since we are right here, we can use this mesh and use it as an input, for instance, tau factor, the software developed by Sam Cooper, who presented on Monday, I think, to get the tortuosity. Or we can use that same mesh in COMSOL and get electrochemical properties. So as you can see, this is what I kind of mean by the artistic workflow and bringing everything together. The idea here is just taking all these different models and tools, etc., put them together in order to generate results in this idea of the battery manufacturing process. However, as I mentioned before, we also have the wonderful work by ABOS. So we can take that structure and actually run the Lattice-Boltzmann model to include here electrolyte infiltration. And then why not using INNOV again and get other estimates of tortuosity, for instance, or electrochemical properties. So as you can see, the artistic workflow basically is this. And give us a lot of flexibility to explore different branches and alternatives for the battery manufacturing process. And also, I want to put this simple idea here that our workflow basically starts from the slurry part, where we have very tiny scales, and we can bridge this with what we get in the end with basically electrochemistry results. So we go from very, very little scales in space and time towards macroscopic observables, that the one we have in the electrochemistry characterization of batteries. So in that context, we believe that this workflow basically is allowing us to study the influence of the different parameters within the battery manufacturing process. So basically, every red arrow here will be some kind of parameter that we can analyze and basically study and characterize to better improve the influence of such parameters in the battery manufacturing process, and of course, eventually developing recipes to improve the development of batteries. In second place, we have also more sophisticated tools that will allow us to carry out this sort of study. So of course, we are working already within the artistic project with Bayesian optimization and machine learning in order to, as I was saying, better understand the influence of every parameter. Also, I believe that the modularity of this workflow, where basically we are connecting different tools, models, etc., is flexible enough to, as I said, explore different alternatives of the battery manufacturing process, let's say, including Lattice-Boltzmann without it, taking account calendaring, not taking account calendaring, etc., etc. And in that sense, also, it's flexible enough to eventually keep adding tools. I, of course, in the future would love to add machine learning components to the workflow in order to see how can also affect the evolution of the whole pipeline here that we have for the modeling the battery manufacturing process. And finally, I would like to put this also in perspective that modeling such a complex system as the battery manufacturing pipeline, it's very complicated because we are, as I was saying, bridging different scales. We are using different tools that have their own reach, again, at different scales. So in that sense, the idea of understanding how errors propagate through this whole workflow, it's very complicated. So I think this workflow would be great to explore in the future the typical mathematical problem of uncertainty estimation in this context. So moving forward, let's discuss now a little bit the idea of building a battery manufacturing digital twin. So as we know here, when we do research in battery manufacturing, we have prototyping units. The problem with prototyping units, it's a practical problem basically, is that we are usually very constrained in terms of manpower. I mean, running experiments requires time, dedication. Also, you are affected by multiple issues, like your measurements might be compromised by errors, etc., etc. So let's say basically that the experimental approach that has classically dominated the process of characterizing batteries to study them might not be able to scale in this current era of big data, where basically we are trying to gather the largest amount possible of results to better understand what's happening here inside of these batteries, right? So with this artistic workflow, we expect to build something that we refer to as the digital twin, or the digitalization of the battery manufacturing process. The battery manufacturing process, as you already saw, it's very tricky because we have many different steps with multiple different parameters, with different effects, etc., etc. So here we can see a flow chart where we see basically many of the different steps that take part in the battery manufacturing process, and that we have sort of addressed before with the artistic workflow. And here in the end, basically, we also add electrochemistry protocols to, again, characterize all this. So with a digital twin, let's say a practical implementation of the workflow that we already shown before, we can scale the study of batteries in this computer-dominated era where data is extremely crucial to that. So of course, the experimental input will be always fundamental to better calibrate the models that we are putting within our workflow. But once we have used such data to, again, high quality data to calibrate our models, then we can have up and running this digital twin, and with that explore as much as possible different configurations with different chemistries, etc., for the whole battery manufacturing process. So this is the fundamental idea behind this workflow and the services that we are going to now introduce in what's left of this talk. So let's go to it, to the introduction of the artistic free online services. So classically, we have an experimental chemist in the lab, but now with this service, we expect that they will move in front of their computers. And from there, they will be accessing the artistic web page through the computational portal, basically to access all this and, getting the results that we have shown for the different steps in the workflow. We will go into more detail in a while to check slurries, structures of slurries, dried electrodes, their structures, etc., etc. So when somebody connects to our web page, eventually they are going to find already in our database some results that we already computed, and they will get an answer right away. If not, and this is the interesting part, the request that the user have submitted to our web page will trigger the simulation of those results with the workflow that we've already shown in our HPC cluster that we have here. In this HPC cluster, basically, we have all the artistic models and tools there, also the typical software required to run these different models, etc. And then, of course, the simulation of the slurry, the drying, the calendaring, etc., will take some time. So the user will have to wait a bit while the HPC cluster finishes to compute the results of this simulation. Those results will be sent back to our website portal, and of course, they will be stored in our databases. So when another user asks later for those same or very similar results, they can have access to them very quickly. And then, of course, the user that was waiting for these results, that for these simulations that were launched as a job in our HPC cluster, they will receive an email notifying them that the results are already available in our computational portal. So this is more or less the, let's say, user interaction that we will provide to the users to, already access the results that are already in the different databases of the artistic project, and also, use the models and the tools that have been already introduced during the week to produce and access new results. So now let's go to the real infrastructure so we can see, to the real interface, so we can see how this is going to look like. So some examples before. Here we have some examples of different slurries, for instance, with different solid contents, with different percentages of active material. And also we can see here how the slurry looks at the beginning, and then how it looks when it's already a dried electrode. So this is the sort of information that you need to keep in mind that you will be able of accessing in this web service. So let's go to see how this looks like. Okay, so here we have the web interface for the slurry. So here you have a README where you can see all the specifics, all the technical and scientific explanations behind the modeling of the slurry here, and also many references that will allow you to better understand what's going on here. Then we have all the different inputs that are relevant to trigger an slurry simulation. Here, for instance, we can see how the carbon binder can be, we have this slider to input different sizes for this. Also here we have the active material, the number of particle sizes that we would like to use to model this. So in this example, we're choosing 6 to model the slurry simulation. And then the user can input the specific values for these particles, first the size, and then the corresponding fraction. And of course, as you can see now, the platform will force you to have a total addition of the different fractions equal to 1. So now we'll see as we go through filling out all the different values for size and fraction corresponding to the 6 particles that we are using in this particular example, that the platform will run this sanity check that I'm talking about of, enforcing that the addition of all the fractions is equal to 1. So as you can see right now, once we have input all the correct values, the platform validates that. Of course, we do that to avoid submitting inconsistent input sets. And then we input values for the dry mass. Again, here we have another slider for the active material. So then we get another warning that you can see below in red, where the addition of the active material values has to be again equal to 1. So here, since we took 85, we moved to 7.5 in additive, conductor, and binder in order to satisfy that condition. And then in the end, we add also a value for the solid content ratio. And this is an example of a whole set of parameters, let's say, that we don't have in our database yet. So after they are all the parameters validated, we can see down how the interface is telling us your slurry is in the queue, so the simulation is running, and you will receive an email when this is actually ready. So now we can move to the second part of another case of slurry. Maybe I'll move forward because, again, this is basically the same. We input the different values in here for the for all the parameters received as input. Again, the slider for active material, the same condition to be satisfied. However, in this case, all the parameters that are being considered as input in here they correspond to one slurry simulation that we already run, and we therefore have in our database. So when we click in calculate, what we will get is a message that tells us that this result already exists, so we can go see it, and also eventually we get next to the next stage, which is drying. So now here we can see how the slurry results look like. So basically in the left, we will have all the different parameters that we input, and then we will get as results the density of the slurry structure. And here we can play with the 3D plot, let's say, of this structure, and also the user will be able of downloading the coordinates and the radii that basically describe and fully describe all the particles considered in this slurry structure. So, and finally, here we have the drying. So as I was saying before, this result already exists in our database, so we can therefore move with drying. So as you can see now, I can click in Go Drying, and what we will get is the corresponding drying interface to launch a drying simulation. Here you can see the different drying approaches that are considered, the different evaporation modes. We also have to define a number of particles at different zones. Also, we have a README like the one we saw before in the slurry section to get all the specifics, and also some diagram that it's there to better understand what's going on here. So then we can go and calculate, therefore proceeding with the drying. In this case, the results for this drying are already available in our database. So again, in the future, eventually we can then continue and go with calendaring. But here again, in the left part of the results, we have most of the input values that we use for launching this simulation. Here we have also the structure of the dried electrode that we can see and play with its 3D version. We can download that structure, and also we have some results here, like the mass loading, the porosity as a bulk, and the porosity as a whole thing. So this is how this web interface looks like, and how basically users can use it to explore different aspects and the corresponding simulations of the whole battery manufacturing process. So now let's move to discussing a bit the conclusions and perspective of this work that has been able of bringing together most of the different results of the artistic team. So in first place, I would like to stress that this artistic online service represents a milestone in terms of the goal that we have of sharing scientific results with the battery research community. In second place, we believe that this platform will also allow us to carry out reproducible research based in the use of these common models and tools. I mean, we have already worked with this. Potential collaborators might use exactly the same models and tools to carry out their own research. And since we know that basically we are working with the same set of tools, we can compare our results consistently and also reproduce whatever different data that they have generated for their scientific work. In third place, I want to mention that the expansion of the artistic online services will continue. I mean, so far I've just showed you the slurry part and also the drying part. But of course, the long-term goal is including all the different components that we saw in the artistic workflow. And in that sense, we expect to really cover the whole battery manufacturing process. And then, of course, that same expansion considers the incorporation of more chemistries, models, etc., since that is something that will be also part of the upcoming developments that we already have in the planning of this platform that we are working in. And maybe finally, two announcements. So as you saw, we have there the button for Go calendaring. So the calendaring step is almost ready to be fully deployed in this platform. So we believe that will be included probably very soon as part of these online services. And in practical terms, the access for everyone to use this tool that you can be able of using after filling the registration form that is available in the artistic website will be from July 5th onwards. So basically, we are working right now in the last details here, correcting some typos, improving the usability of the interfaces, and we are really working for having this tool up and running and sharing it with all of you. So I hope that all the attendees of this webinar will be interested in using this super powerful tool, and therefore considering the different results developed by the artistic project to be part of the different research projects that they are carrying out. And with that, I'm happy to answer some questions in case there is something there. Thank you.
Thank you very much, Fernando. So yes, I see. Well, wonderful presentation. So as you mentioned, yes, it's a very important milestone of a project, right? A very important deliverable. The intention here, of course, is completing also with the infiltration model that Avos was presenting earlier this morning, and Oyer also presented yesterday. We also have the intention to couple with the electrochemical performance simulator online. This is also a tool that we already have. And and please remember that Innov, which is this wonderful meshing tool that Mehdi showed on Wednesday, so it's already available online. So it's free access for everyone. So you just need to go to the web page of the project, computational portal link, and create a request for a password. You will receive a password, and then you will be able to use this Innov. You can also explore the data we already have in the generating the project. So right now we have more than 200 users for the data explorer that we introduced in the webinar series of last year. And soon, as Fernando mentioned, so 5th of July, so you will have access to the computational tools simulating the first steps of this lithium-ion battery electrode manufacturing process. Okay, we go maybe for questions. I see.
Yes, let's check. We
there
have
is Elisabete, so I put
exactly.
there. So yes.
She asks, do you aim to include the aging data into the software? My little grain of
maybe
sand,
I can answer. Well, the artistic project is not dealing with aging. So what we are intending to do in the artistic project is demonstrate the link between manufacturing parameters and electrochemical performance, the first cycles. Of course, when we are talking about manufacturing, we should talk also about formation step. So this is something that we are able to model, and we have a paper recently published on that. It was mentioned briefly by Mehdi in his presentation Wednesday. So this will be included for sure, but not the long-term aging, right? Because this is out of scope of what we're intending to do here in this project. But it's a good question, yes. Okay.
Okay, here we have a question from Rubayat Mahmoud, who asks, do I have access to, I already have access to the artistic portal. Do I have access to the workflow yet, or should I have to wait until July 5th? Yeah, I think you have access to the whole system, but you will find the link to actually access this tool from July 5th onwards.
Exactly, yes. There is, also some, Serian says, super web app, very compressive interface. Thank you, Serian, for the nice comment. So another question, can we use this tool to generate the electrostructure and export it in a format supported by other FEM codes? Excellent question, Binshak. Maybe you want to answer, Fernando, or I can answer, as you want.
Let me reread this. Can we use this tool to generate the electrostructure and export it in format supported by all? Well, to be honest, I mean, yeah, I know the answer, but
I can answer, yeah, because so Binshak, so what Mehdi Shushan showed on Wednesday is Innov web app, which is actually a web app that allows you to generate electrostructures and to treat the electrostructures generated from this physical simulation of manufacturing process to import them, the structures, in any kind of FEM software that you want. Of course, Mehdi showed that it's possible to export in any kind of, most known formats. Of course, console multiphysics, but also formats that can be used in FreeFEM, any kind of Phoenix, any kind of software that people is using for FEM simulations in 3D, right? Because here the outcome of the simulators is 3D structures, right? So then in order to do so, what we need to do right now is using the manufacturing simulators that Fernando was showing here. Thanks to this manufacturing simulator, you will produce electrostructure. You will need to download it, right? And then import it. So in Innov web app, right? That is in another part of the web page of the artistic project. For now, you will need to do in that way. But in the future, as Fernando mentioned, so Innov will be integrated in the workflow, right? So I mean, this meshing procedure will be automatic, right? Right now, you need to do it by hand, but by using Innov, which is already available in the website, right? So yeah. Thank you, Bishan, for the comment. So okay, so I'm done answering. So do we have more questions, maybe from the attendees?
Let's see. No, I don't think we have more questions.
Yes, I think maybe you can write in the chat, well, from where are you from and so on, because I used to ask that at the beginning of each session, but this time I didn't ask. I mean, some of you already say, so yeah, I think we have an answer also from Mehdi.
Yeah, Mehdi is trying to say something. I will read it. Mehdi says, you can export the mesh as Nastran, so a .bdf file that should be recognized by most of the softwares. Also, as the native format of console, .mphtxt, or as a matrix.mat. So you can convert it into the desired format in MATLAB. So I think Mehdi is saying, like, basic, and also, as Alejandro was saying, you just get the structural electrode and from the platform that I already showed, and basically with Innov, you can export to different formats that will be useful for your research.
Yes.
Yeah, he agrees. He says that yes, .bdf or .mat works fine for me. Yeah.
Perfect. Great. You know, the intention of this platform is to make accessible the models to experts, for sure, the people that are doing models and so on, but also to no experts, and in particular experimentalists. Because we want to work hand by hand with experimentalists here. So we want to somehow generate 3D electrostructures from the manufacturing simulation that can be used for analysis of electrochemical performance and also for analysis of the results that can come from tomography, right? I'm sure that Paul is going to show very beautiful images from tomography characterization. So it is exactly what we are doing here, but from the simulation of the manufacturing process, right?
So we also have a question from Tom Tranter, who asks, have you considered adding pore network modeling into the workflow?
Well, very nice question. So, yes, actually, you know, in some part of our analysis, we are using pore network modeling. In particular, I would say it's more pore network analysis to extract the pore size distributions, right? And also to calculate properties such as the tortuosity factor and stuff like that. So it's something that is implicitly integrated in the workflow. I would say it's more the offline workflow that we are using here in the lab, in the research side. But it's, as Fernando mentioned, so this online workflow will be modular, right? So, and we can include, the idea is that we can include in the future other extra features. And also the vision of this platform is that it will become open, right? So in the way that other people, you know, maybe like you are developing maybe a specific tool and you want maybe to integrate this tool in the workflow, and this will become possible, right? This will come in 2023, right? By the end of the project, this feature. But here the intention is something I mentioned also in the webinar series of last year, is having a kind of Wikipedia of battery manufacturing data and battery manufacturing simulations. So that means an open platform, a collaborative open platform around this topic, right? Trying to merge the two communities, the experimental one and the modeling one.
Absolutely. I mean, I want to add there that, again, as you mentioned, this workflow is highly modular. So if somebody else out there wants to collaborate and they already develop a model for something that can be included in this workflow, yeah, you can send it to us and we can put it there and see how that works. So yes. I think, Alejandro, as you are saying, even more, you can, for instance, well, maybe Theo will take the word in a while. Theo also has different models of drying, something that actually I should have mentioned and I didn't. He has an homogeneous and an inhomogeneous model for drying. And so the whole idea is actually having an array of different codes or models for different processes and actually then explore how different combinations may lead to different results, right?
Exactly. And even more, so exactly. So we will allow people to upload their home by themselves, right, and testing by themselves their home developments, right? So it's kind of collaborative modeling platform, you know, that we are envisioning in the future.
Mm. So let's take this next question. So I think we can also have probably the input of Theo here, because Nivedita Kulkarni asks, what are the current limits of the models, such as the maximum size of electrode, battery chemistries, etc.? So we have a few battery chemistries, and in the more, of course, new ones will be included, but in this technical question, I think Theo needs to give us his perspective.
Yeah. I mean, maybe I can comment before Theo. Of course, Theo, you are welcome to comment. Alan also, for sure. But here until now, so it was shown also by Theo, Alan, and so on. So we are working on NMC 111, right? This is a material that we have already successfully simulate the manufacturing process, validate experimentally, of course, including using tomography, as Paul is going to show later on. We are also working on LFP, right? We are also working on silicon graphite and graphites. So Theo also show some preliminary work on organic electrodes, organic materials. I mean, for electrodes, for lithium-ion battery electrodes. So yes, the idea is having kind of chemistry neutral approach. I mean, the methodology can be adapted to other kind of chemistries, right? It doesn't mean it's easy, because every time you are changing the chemistry of the slurry, you will change the rheology. This is something that Bernard also illustrated very well in his presentation. So you will need some characterization in order to extract the parameters that you will need to put in the force field that you use in coarse grain MD to simulate the slurries, the drying process, and so on and so forth, right? Theo, maybe, and Alan, maybe you can comment a bit more on this next question.
Yeah, if I can. So the only thing that I wanted to say is the following. Actually, for the moment, the platform has some limit that we put, okay, as for instance, we put only an NC 111 or a limit for the mass that you can simulate, etc. But the idea is
I think we lost Theo, right?
Yes, we lost you, Theo.
Okay.
Alan,
Sorry.
you want to mention something in the same?
And there, I don't know what happened.
There
Okay,
you're back, Theo.
Sorry.
Theo's back. Yes.
Yeah, sorry. So the overall idea of this this platform is to give you really the freedom of do whatever you like. Okay, so all the limits that we put are either because the model is not really ready yet to be open to everyone, so we should still adjust something. But for instance, also the model that I presented on Wednesday, so the new evaluation model is already there. So even all the things that that are ready to be put are already there, and the other limits are just say limit to avoid people to wait too much, meaning that if you allow, for instance, to simulate really a big system, the simulation will take really long time. So the idea was also to have a compromise respect the waiting time of people because the resources are needed and the freedom of choosing whatever parameter you like. But still, you can really play with any particle size distribution. You can consider we start typically we work with a mass simulated mass of 0.1 milligram for the electrode. Here you can go up to 0.2. So you really are free to do a lot of, the degree of freedom I think is not a problem. All the limits that you put just to avoid waiting too much or because the models that we will add are not ready yet to be made public, let's say.
Exactly. So you should see also this platform as a demonstrator, right, of the full capabilities of our simulation tools, the simulation tools that we're developing in the project. And of course, I mean, some people of industries attending this webinar series. So of course, I mean, these models, they can be tuned to a specific request, right? So, but of course, we are not disclosing that. So we are here disclosing the models with the parameters that we have actually explored from an academic point of view, right, to develop the methodologies, right? I think we have more questions.
Yes, we have one question, but I think the answer is very short. Does the model work for all solid-state batteries?
Yes and no, I would say. I will answer this question. Sorry, Theo. I will take over. So definitely, I mean, if we are talking about slurry and so on, if we are talking about maybe a wet process of solid-state batteries, why not? I mean, we could maybe think adapting this approach to solid-state, right? The calendaring step definitely can be transferred to solid-state batteries. This is something that we are going to start. I mean, we're going to start to work on that in next October. So I'm welcoming my group, so a new PhD student on that. So this is very nice. Then Innov software that was presented by Mehdi on Wednesday, so is able to generate already electrostructures for solid-state batteries. I mean, he mentioned that briefly. He provided an example in the paper we published with Mehdi a few weeks ago. So there is an example of solid-state batteries. In that situation, the electrostructure is generated using a stochastic algorithm. So the 4 electrodes are generated randomly, right, by placing solid electrolyte, active material, carbon additive, and you can also tune the amount of porosity that you may have, and if you don't want, maybe in a solid-state electrode, you can plug this as an input. And then so the algorithm generates the electrostructure, right? So you can play with particle size distribution there. You can play with the degree of overlapping between the particles. You can play, of course, with the formulation. And this is, it's possible through Innov, but you will not have a prediction from the manufacturing process simulation of the electrostructure. So it will be generated stochastically. However, some of the tools that we are releasing here, so they are able to be adapted, I mean, to simulate solid-state processing. And just remember also, maybe if you check our publications, you will see links to the GitHub. So in the artistic project, we have a GitHub page where we are putting all the codes there, okay? All the codes that we are developing with some few examples of parameterization, right? But if you really want to do, exploit these models in almost full potentiality under the restrictions that Theo mentioned, you should use the online service, right? At some point, so this online service will become, you will not need anymore to request a password and so on. This will be in the future, I think by the end of the project, 2023. But right now, so we want to proceed in this way because we want to assess the impact of this work that we are doing in the project in the community, right? So now I can say that more than 200 people is using the Data Explorer that is just exploring the data of the project. And this, it's very nice to see that part of these people is from industry and most of the people is from academia. And well, it's a way also for seeing, I mean, how impactful is our work in the community, right? And I really appreciate, I really acknowledge all the people who are using this this data explorer already. And I also receive many emails from people, suggesting maybe improvements, or suggesting things that we can add and so on. I really appreciate it. It's really the spirit of this project. So creating this collaborative platform of battery manufacturing simulation online. Yeah.
And if I may jump in, actually, also relates to the limits, etc. The idea of this is really to create a collaborative database, meaning that we didn't test all the parameters that you will be able to play. For instance, the particle size distribution, we could not test any possible particle size distribution. So you could get results that we never get those kind of results. So it's the idea really to build something in a collaborative way. And if for a condition that we never tested, there is any kind of problem or whatever, we will be really happy to have your feedback also to improve the model and increase this dataset size, again, in a collaborative way.
Of course, yeah. And also something that was also mentioned by Fernando in his presentation is the problem of uncertainty propagation, right? When you are coupling models at different scales, describing different steps along the manufacturing process. So it's very important to have an idea of how the maybe uncertainties that you may have in coarse-grained molecular dynamics simulations will impact the electrochemical performance prediction, because in coarse-grained molecular dynamics, so you are starting from a random distribution of particles, in the volume, right? And it's something we study also in 2019, and we published a paper. It was also presented in the last webinar series of 2020. You can check the videos, the corresponding video of the talk. I think it was my talk in the webpage of the project.
Yeah, maybe I will just also add to this that, I think the current most significant problem in science, maybe in general, it's actually uncertainty estimation, because we are working already with complex systems for which we have data. We are better understanding them through, for instance, machine learning algorithms that are black boxes, where we don't really understand what it's happening inside. This is a transversal problem in all the sciences, I would say, now, given the major relevance of data sets. So in that sense, I think this particular problem of battery manufacturing with a workflow behind it, it's the perfect problem also, or context or situation that, if it's successfully addressed, can also provide solutions for other types of problems of related disciplines, etc., etc. So I think it's a super motivating and interesting problem in that context.
Yes, and also I can share one email I received from one of the users. Asking, okay, are we planning to add also machine learning services, in the platform? The answer is yes. The same comment as before. So the machine learning models that we have, present in this webinar series, in the previous one, our papers and so on, they are all accessible through the GitHub page of the project. Okay, so we systematically publish these algorithms together with the papers, right? So you can reuse it for your research and so on and so forth. But also we will embed some web apps in the artistic web page that also you will be able to play with them to predict the influence of, for example, calendaring conditions on electroporosity, tortuosity, and so on and so forth. And connected to that, also, I strongly encourage everyone to attend my lecture. After the one of Paul, that is about the use of these machine learning models in the place of experimentation, thanks to the use of HoloLens technology, so mixed reality. You will see. Yes, also there's another dimension, of the project that is a bit orthogonal to these online services, because in that situation, you basically use the models in the place of experimentation, right? With that digital information superposed in the real world, right? But you will see the demonstration afterwards.